Hey guys, welcome back to the Beginner's Guide to Restoring a Classic Black and White TV from the late 40s. I'm picking up right where we left off, which is checking out the chassis. In the last installment, we looked them both over, did not see any concerning issues, took a little look at the schematic. In this installment, I'm going to try powering this up. I've also done a bit of cleaning. So Windex on the tube glass, a damp rag on the chassis just to get some of the crud off. I want to be able to see inside the tube, see how the filaments are glowing, look for any issues like red plating or a blue glow. But before we dive into this, I want to take this opportunity because I have some other Admiral chassis that were sold at the same time to compare and contrast and show you where marketing meets engineering. So this was their 30 series chassis. This was top of the line. The 30A, 30B, 30C. We have two beefy power transformers. Well, there was also a 20 series, a 20A, a 20B. This also has a separate power supply. Notice a difference. What happened here? Where'd this guy go? It's a very similar design, but they cut a few corners. It doesn't have that little selenium rectifier for the negative voltage. I think they cut out one video IF stage, and they used a less robust power supply. Notice this guy's a little bit bigger. This is supplying all the power for the set, and they get the lower voltage. They use a voltage divider. They burn off some energy to get the lower voltage they need. Actually, they use the Class A audio output tube as a stacked power supply design, they call it. And a few other little bits. In other words, they chipped away at the design a little bit, made a few compromises to lower the cost. So this would be for their mid-range sets. And then there's the 20X series, 20X, 20Y, 20Z, which doesn't have a second chassis. Everything is on the main chassis. This is one that's given to me for scavenging parts from. This has a single power transformer incorporated into the main chassis with a socket right on top of it, and the rectifier tube sits right into it. This has even more corner cutting techniques. Even the high voltage cage is bad. Part of this was to save money. Part of it was they used this in some tabletop sets, so they had to make it smaller. Fewer tubes, fewer IF stages. I think this has 3 video instead of 4 video. So I just wanted to show you that even back at the very beginning of TVs, they were already cost conscious and doing what they could. So this, if you're going to have to choose between an Admiral and you have a choice between a 20 series, a 20A series, a 20X, or a 30A, 30A is the best performing. But it's also heavier, has more tubes and all that. Alright, let's focus back on our set. Powering up an unrestored vintage tube device is generally not a good idea. The advice you typically see is don't plug it in. Don't plug it in until a qualified service tech has gone over it. True, and that's the safe, easy advice to give online when people ask, is it safe to turn it on? Partly because it's true to some extent, but also when you're putting a small message online, you're going to take the more cautious approach and just tell somebody don't do it without going into depth of why you shouldn't do it, what to look out for, are there exceptions. That's what I want to talk about in this video. Generally, I don't so much, because when I decide to work on a project like this, I'm going to make it work, whatever it takes. I don't really care if I can get some life out of it now, because in my mind, I've already planned ahead. I know I'm going to be replacing stuff. On the other hand, if you don't have much experience and you want to learn some troubleshooting techniques and whatnot, it can be very educational to do it. But you do need to take some precautions. People are not wrong in saying that if you just plug it in, some bad things can happen. Yes, they can. The easiest precaution you can take Well, one, which we've already done, is look it over. If you see anything concerning frayed wires, charred parts, stuff that's missing, some dangling wires, some unfinished repair work, don't even think about it until you've addressed those issues. If it's like this, where it looks like it's barely been touched by a human hand since it was made, it's a little more encouraging to give it a shot. I don't expect this to work perfectly. I don't really want it to, because then we'd be done with the series. We want to be able to have some stuff we need to fix, and I can guarantee you we will. So why would you ever want to bother? One, just for the thrill of it. Two, if you can, controlled carefully, eke some life out of it. Get some glow on the CRT. Get some sound out of the speaker. You've just verified a lot of stuff is good, and you can save yourself a lot of testing. If you had a glow on the picture tube, you know the picture tube has some life. The flyback is working. The deflection yoke is working. And the horizontal oscillator is working. The vertical oscillator is working. A lot of stuff. If you can get a rectangle of light on that CRT, you've just checked off a lot of things. The power supply is working. If you can eke out a little bit of an image and a little bit of sound, you know that virtually every circuit in the set is working to some extent. That's fantastic. That is your ideal situation. That's what I'm hoping to get out of this initial power-up. Yeah, I expect it to be blurry and not fill the whole screen and bad audio and all that. But if we can get a little bit of everything, that's fantastic, because then you can start replacing things one at a time, and ideally it slowly gets better. Same goes for a radio. You turn on a radio with a dim bulb tester, being an easy way to do it, and it sounds lousy, but you hear something. That's cool, because then as you replace parts, it starts getting better and better and better. And that's where the fun comes in with the hobby, I think. Okay, so I mentioned dim bulb tester. What's a dim bulb tester? Dim bulb tester is a really simple current limiting device. You simply, instead of plugging your item directly into the wall, you plug it into a box that has a light bulb in it. That light bulb goes in series with the power going to the set, meaning all the current going to the set has to go through the filament of that light bulb. The idea being, if there's a dead short in this, the light bulb will just glow really bright and act as a regular light bulb, and it's going to limit the amount of current going through this set and prevent any damage. So what could be bad in this that would cause damage? Well, if there was a shorted turn inside the power transformer, there was a dead short in these electrolytics, and these are the most common issues you're going to see that would cause a major problem, is going to be this, the power supply. Bad power transformers, shorted filter choke, shorted electrolytic caps. Basically, any of this stuff being bad. A tube could be bad. It could be shorted out internally. A dim bulb tester is a really low-cost, effective way to protect it. Now, if you're used to working on radios, you might be used to using a 60-watt light bulb. TVs draw a lot more current. Even if the TV is working fine, if you put a 60-watt light bulb in series with it, the TV is not going to be able to work properly. The light bulb is going to be choking it of the amount of power that it needs. Whiteboard time. I'll explain briefly what a dim bulb tester is and a little bit about how the device I'm going to be using operates. So, pretend this is our TV, and this is our wall outlet with 120 volts AC coming out of it. We want to put something in between this and this to limit the current in case there's something wrong with this. So that's where a dim bulb tester comes into play. On one side, we're going to have a cord that plugs into the wall. Now, on most devices from the era when this was made, they had non-polarized plugs. The hot and neutral were interchangeable. Things have changed nowadays. Basically, everything has a polarized plug, meaning it only goes into the outlet one way. The wider blade on the plug is your neutral. The narrow is the hot. So if you're going to build one of these, I would recommend you set it up so that the neutral just goes straight through. So this is my little interpretation drawing here of a receptacle. So you're going to make a box of some sort, and it's going to have an outlet in it. Buy yourself a duplex outlet at the hardware store. Take the neutral side and wire it up to a power cord. Buy a replacement lamp cord, something like that, and have the neutral just connect straight to it. Put this in a nice box, insulated. And you're also going to want to pick up a light bulb socket. Standard incandescent type screw base, like for a 60-watt bulb, and that's going to go into your hot side. So instead of this going straight through, I'd suggest you add a power switch, and then add provisions so you can have a light bulb and connect that there. And here you're going to put your light bulb, be it 60 watt, 100 watt, 150 watt, whatever it may be. So that'll be your light bulb. And this plugs into this. So how does it work? Well, so we have our TV plugged in here. If this draws way too much current, this is going to light up. Light bulbs have a negative temperature coefficient, or is it positive? Well, the resistance goes up with temperature. I guess that's be a positive temperature coefficient, huh? So these are somewhat inherently self-current limiting. In other words, the more current that goes through them, the hotter they get, the more resistance they have, which fights against more current going through. So we get some protection from just that feature. But also this just has some resistance, which will resist current going through to your device no matter what. So that's all it is. That's what it comes down to, is we have something in series between the wall and our device that will resist the flow of current. And the more current this draws, like imagine this is just a dead short. Well, this will just be like having a 60-watt light bulb plugged into the wall. No big deal. The current won't go through this. It'll go through the light bulb and get shunted. So say there's a shorted electrolytic cap, it'll just go. Most of the power will be burned up here, and a little bit will trickle through that and go back around. So that is all there is to it. So if you want to build one, get yourself a little box, get an outlet, get a light bulb socket, get a wall power switch. Alright, I'm going to be using something that has a bit more going on. It's a Sencor PR57. It is a combination Variac isolation transformer with a circuit breaker and a fuse and an ammeter and a voltmeter. You can check both the voltage coming into it and the voltage coming out of it, the current flowing through it, and you can vary the voltage coming out of it. Now, just like this dim bulb tester, it also has an outlet on it that you connect, and you plug your device into it, but it has an isolation transformer, so there is no direct connection between these. This goes right to a transformer, which is a Variac. So the other side of it goes, and it has a fuse, and it also has a circuit breaker. Forgive me, I don't know what the symbol is for a circuit breaker off the top of my head, but something like that. And it goes to this. And this has a wiper on it, so actually this isn't quite accurate. It's more like this goes to a wiper, and there's a big knob on the front, and you can vary this contact point across here, which varies the output. It can go from 0 to about 140 volts AC with 120 coming in. And there's actually also an ammeter in series with all this stuff, and you can have the voltmeter either on this side or on that side. It's a luxury to have, and you can certainly build your own. Go out and get yourself a Variac, get an isolation transformer. They're often two separate things. You can't really do it in one shot, so there'll be no isolation transformer, and then after that, a Variac, and then you get an ammeter and a voltmeter and switch it and rig it up, and you can find plans for that online as well. Perhaps seeing a Homebrew Variac setup would be useful. And here's one I got out of an estate. Fuse. Variac goes from 0 to 120, controls the output voltage. Power switch, indicator light, and a voltmeter goes 0 to 150. It shows the output voltage. Here it is on the back side. It's a pretty beefy setup. I'm sure it's at least 5 amps, if not 10 or more. Big, chunky power cord. This would plug into your wall outlets. The devices you want to control would plug into these outlets. And here is the back side of a Variac. We have a bunch of turns of wire around an iron core. When I rotate this knob, it moves this big wheel that has a chunky carbon contact. As I rotate it, it controls where on this coil we're pulling power from. That will vary the voltage on these outlets. But before we even do that, I'm getting ahead of myself. There are some even more basic things we can do. Easiest thing you can do is pull these tubes out. Pull these rectifier tubes out. If I hook this up to the main chassis and turn it on right now, there will be no B+ supply. There are no rectifiers. But there will be power going to the tube filaments. So if all is well and I plug this in and turn it on, all the tube filaments should glow. The normal level, which is a sort of a dull orange. That's what we're going to do. Now notice I still have the cover off the high voltage box because I want to see what's going on in here, but that means I have no power cord. Well, that's where one of these comes in. I call it a cheater cord. It's essentially the same power cord that would be attached to this box, only it's not attached to anything. They actually sold this as a replacement for the main power cord in case it went bad. We TV techs affectionately call them cheater cords because it lets you cheat all the safety devices, and you can do that while you have everything exposed. But we know what we're doing. We're safe, so that's what we're going to do. Okay, I have this PR57 Variac turned off, and we're going to plug that in. I'm going to turn the set on. I'm going to use the power switch on my Variac rather than to keep relying. Well, one, I don't even know if the power switch is good on this thing, but I feel safer using that power switch. Alright, so it's definitely on. Let's reduce the lighting so we can see the tubes. And here we go. I have this in current mode, so we'll see how much current it's drawing. I already know it's dialed into about 117 from my previous use of it. The needle on the meter slammed over when I turned it on. That's because when tubes are cold, they have very low resistance. But now it's settled in pretty comfortably to around mid-range on the meter. It's 3/4 of an amp, which seems reasonable. And I think you can see that tubes are glowing. So it's a 6Y6 audio output tube. That one. It's going to be one that's pretty easy to see. That's your normal color. Call it a dull orange. And on the main chassis, we have plenty of stuff glowing here too. It's our 5V4 damper tube. That's, I'm not sure, 6BA6, something like that. Anyways, everything is glowing, including the CRT, which is really hard to see. Fantastic. If you really wanted to check the current draw, you could look up the tube data for all these tubes, see how much current each one draws, add them all together. That should match our total. But I'm just going by color and my experience, and that looks good. So now we let this sit for 20 minutes or so. I'll check every 5 minutes or so and see if the power transformers are getting warm. Alright, it's been about 20 minutes. Everything is cool, running 3/4 of an amp, full 117 volts in, all tube filaments are glowing. So let's shut this down. We're going to pop in both the rectifier tubes and the field coiled speaker. I'm going to hook up a voltmeter to the main B+ out from the larger power supply. Now we're going to turn our Variac down to around 40 or 50 volts. Put it back on. We're going to monitor the current.